Oh, hi everyone. Welcome to the first high energy seminar of the semester. Welcome back after what was hopefully a great summer for everybody. So we will start with our talks in a moment. Just a couple of announcements before we do so. We are still filling our speaker schedule. So if you have any recommendations for people to speak, or if you yourself would like to give a talk, please let us know. And the other thing is we encourage everybody to ask questions. You don't need to wait until the end of the talk. You can always, like even during the talk, if you think of something, please feel free to put your questions in the chat and we can read them out at the end, or you can wait till the end of the talks to ask your questions. But yeah, if you think of something in the middle, please feel free to put it in the chat. So without further ado, let's get started. Our excuse me. Our first speaker today is Dr. Biny Sebastian. She is a postdoctoral research associate working with Matthew Lister at Purdue. She did her PhD at the National Center for Radio Astrophysics in Pune in India with Priti Karb. And for her PhD, she aimed at disentangling the contributions of star formation and AGN activity using radio polarimetric observations. She has extensive experience dealing with radio data at high and low frequencies. And today she'll be telling us about her thesis project. So please take it away.
Thank you, Ritu. Okay. So, hi everyone. So, thank you for the opportunity to present my work for this high energy seminar series. I'll be talking about the work that was carried out as a part of my thesis, and this is the list of collaborators involved in this work. The main aim of this work was to understand the origin of radio outflows in Seyfert galaxies and to disentangle the contributions from star formation and AGN. So, despite several decades of research in the field of AGN jets, there are still a lot of things we do not know about them. So we know that only 10 to 15% of AGN host large-scale jets. So why is it that only some AGN host jets that extend up to kiloparsec scales, whereas most of them don't? What are the factors that affect jet formation? Another question is regarding their duty cycles. For how long does one episode last, and how often do they restart, and does it depend on the type of AGN and so on? How much of the jet kinetic energy is being fed back into the host galaxy? So, majority of studies trying to understand jet formation have had their focus on powerful jetted systems. We, on the other hand, were mainly looking at Seyfert galaxies, which are classified as radio quiet. So I would like to mention that it is just as important to study weakly jetted or radio weak systems as much as the powerful jetted systems if you want to get the full picture. So it was known from high angular resolution studies of Seyfert galaxies that they host or show radio structures on 10 to 100 parsec scales. So some of them showed double structures, some of them had triple structures, which were immediately suggested to be evidence of jets. Then the question was, why do Seyfert galaxies not host kiloparsec scale radio jets like those seen in radio galaxies? So Baum et al. 93 and Colbert et al. 96 carried out lower resolution studies of these objects using the VLA, and what they found was that most of these galaxies actually hosted kiloparsec scale radio emission. But again, the origin of this kiloparsec scale radio emission was not readily attributed to jets. For example, Baum et al. Suggested that the radio emission is coming from starburst-driven winds, and whereas Colbert et al., who had a comparison sample of starburst galaxies along with the Seyferts, claimed it's more from a jet-related origin. So Gallimore et al. 2006, who had a larger and a complete survey of Seyfert galaxies showed that more than 44% of Seyfert galaxies show kiloparsec scale radio structures. Again, although they preferred the Asian origin, the study was not conclusive. So before we really get into understanding jets and feedback in these systems, we need to disentangle the radio emission from jets versus from other possible contributors. So now I'll talk about the possible pathways or mechanisms that are discussed in the literature which can lead to the radio emission that is seen. So the first one is the starburst driven winds. So what happens here is that the star formation that's going on in the center will lead to supernovae and stellar wind, which will in turn lead to galactic superwinds. So one can see here shown in purple are the emission line H alpha plus N2 winds from the prototypical starburst galaxy M82. Another possibility is that Asian winds. There are several mechanisms that can give rise to an Asian wind. For example, radiation pressure driven, thermally driven, and magnetohydrodynamically driven. And the last possibility is that a jet itself is responsible for the radio emission, which is similar to the radio galaxies. So in the case of jets, the radio emission comes from the central engine itself. So with our study, we are trying to address the question of what leads to the origin of radio emission, which is outflow like in Seyfert galaxies. Is it star formation, or is it shock acceleration by winds or Asian jets? In particular, can we make use of radio polarization to disentangle the contribution from jets versus other possible contributors? So to answer these questions, we observed a sample of 9 Seyfert galaxies, along with the sample of 7 starburst galaxies using the EVLA in full polarization mode at 5 and some at 1.4 gigahertz. On this slide, we present some of the EVLA images from our study. The background shows the color composite image of the optical host galaxy, whereas the white contours represent the radio continuum emission. The 4 on the left are starburst galaxies, whereas those on the right represents some of the Seyfert galaxies. So as is evident from the images, the radio emission closely follows the optical features and the star formation disk in the case of starburst galaxies, whereas in Seyfert galaxies, they show lobe-like features or codominant features, which and these lobes do not have evident counterpart in the radio. So we detected polarization in only 4 Seyfert galaxies and in 1 starburst galaxy. This might be due to a variety of depolarization effects that are at play. So we further observed these sources at 10 gigahertz. Our initial analysis shows that most of these sources indeed show polarization. I will now talk about NGC 3079 in a bit more detail, which is both the star forming as well as a Seyfert galaxy. The new EVLA image at 5 gigahertz of the source is shown on the left, whereas the spectral index image made from archival VLA data is shown on the right. So the red vectors represent the inferred magnetic field vectors. So it can be seen from the images that the red vectors are aligned parallel to the lobe or the ring edges. Also from the spectral index image, it can be seen that the lobe edges show some flattening of the spectral index. So the high fractional polarization along with flat spectral index and the magnetic fields aligned along the edges point towards a shock origin of the radio emission. So the shock acceleration could lead to a flatter spectra, whereas the shock compression could lead to magnetic field amplification. Another possible mechanism is that there is entrainment of the relativistic materials and magnetic fields from the star formation disk itself, along with the superwinds. So it's well known that this galaxy hosts superwinds. So on this slide, we show the X-ray and emission line contours overlaid on top of the radio continuum emission. The blue contours represent the H alpha plus N2 emission, whereas the magenta contours represent the Chandra emission. Both the Chandra emission and the emission line filaments were seen to be very well correlated with each other. But one can see that the radio and the thermal emission filaments are not very well spatially correlated. The radio emission peaks to the north of the peak of the other two emission regions. Also, if we look more closely at the filaments, the middle radio filament is slightly offset from the H alpha and X-ray filaments. Whereas in other typical starburst galaxies like MAT2, where entrainment is considered to be the primary mechanism, the radio and the X-ray emission are spatially very well correlated. So since in NGC 3079, we don't see such a the co-spatial nature, we believe that this is not the major mechanism of that is at play. Moreover, another important factor is that NGC 3079 shows radio excess compared to the radio FIR correlation, which is also not expected if the material is just being transported from the star formation disk. So we then further looked at the rotation measure images. So Cecil et al. In 2001 had found that the rotation measure undergoes an inversion in sign as one moves from the inside to the outer edge of the northern lobe. So in the rotation measure image that we produced, which was at a slightly higher resolution, we found a similar inversion in RM values, also in the individual filaments. So this does not favor a scenario where shocks are involved. This favors a scenario where magnetic fields are more organized. For example, like helical fields can explain such an RM structure. So now that we have ruled out both shocks and disk entrainment, we are left with the possibility of jets leading to the radio emission. But again, the morphology, especially the H-shaped structure and the ring, everything is not typical of radio galaxy like an FR1 or FR2 type radio galaxy jets. So it was pointed out by Henriksen that such dome-shaped structure and the active regions in Sun could be reproduced by some of the solutions of force-free magnetic fields in the galaxy. So we conclude that while the electron population itself is being majorly fed by the jet, the entire morphology probably is a result of an interplay between the jet and the superwinds, and also the large-scale magnetic fields that are threading this galaxy. So now I'll discuss the polarization properties of the entire sample. So like I had already said, we have detected polarization in 4 of these Seyfert galaxies in our sample. So Seyfert galaxies showed a wide range of polarization fractions. Some of them had 20%, some had 30%. And NGC 438, for instance, had 13% in the inner lobes and 24% at the edge. And at 1.4 gigahertz in starburst galaxies, we detected marginal levels of polarization, about 1 to 4%. So what we can conclude is that our data suggests that the Seyferts show more fractional polarization compared to starburst galaxies, given the resolution and frequency of our observations. Now, regarding the polarization structure itself of Seyferts, in NGC 4388, the inferred magnetic fields are parallel to the lobe edges. Here you can see the electric polarization vectors. They are perpendicular, implying that the magnetic field vectors are parallel. On the other hand, the inner lobe region show polarization vectors perpendicular to the lobe axis, which implies poloidal or longitudinal magnetic fields are dominant. So we compiled our results along with what was present in the literature. We looked at more individual source studies, and we found that the most common feature was the parallel magnetic fields along the lobe edges. Other than the polarization, we also looked at few other properties, sample properties, like radio FIR correlation, which is shown on this slide. So the red and the yellow dots represent Seyfert galaxies, which had kiloparsec scale radio emission, and the black dots were those which did not have kiloparsec scale radio emission, I mean Seyferts. And the stars were basically the starburst galaxies. The purple and the green stars are those starburst galaxies which had superwinds in them. So what is immediately noticeable is that the Seyfert galaxies with kiloparsec scale radio emission lie above the 3 sigma line. So this was also previously noticed by Gallimore et al. So that rules out a scenario where the radio emission is merely a result of winds that transport material from the star formation disks. But from this plot, we also notice that the starburst galaxies with superwinds, but not hosting an AGN, also tend to follow the radio FIR correlation very closely. So what this means is that even though there are supersonic winds, such winds are not often strong enough to reproduce the radio emission through shock acceleration. So hence it's likely, or like it's not as comparable to the radio FIR emission. So hence it's likely that the radio excess in Seyferts is related to jets. So we cannot, however, rule out any magnetohydrodynamic AGN winds. After this, we also tried to see if we could quantify the contribution from each of the possible contributors, like the jet and AGN accretion activity and the star formation, at least using order of magnitude calculations. So there are several studies which help you to estimate the jet power given the radioluminosities. So we used the Merloni and Haynes to estimate the relation to estimate the jet power. So we plotted it against the rate of kinetic energy injected due to the AGN accretion, which was estimated as 5% of the AGN bolometric luminosity. So we see that there is not much correlation between these two parameters, but we were not really checking for correlations. We wanted to compare what is more prominent, if it's the jet or the AGN accretion. So the line is the line where both these quantities are equal. So you can see half of them are above and half of them are below. So that suggests that the contributions are comparable. So similarly, we also looked at the mechanical power contribution from star formation and compared it with both AGN accretion and jet powers. We see that in our sample of Seyfert galaxy that the contribution from all three mechanisms were comparable. And so even though we suggest that the radio synchrotron emission has its origin mainly from jets, the further evolution is probably heavily influenced by other mechanisms as well. Also from this plot, it's evident that the star formation rate and the AGN activity are not correlated. So does that imply there is no evidence for AGN feedback for our galaxies? So similar conclusions were reached by other studies as well. For example, Jarvis et al. 2020. Another interesting result that we see from our sample of Seyfert galaxies is that most of the Seyferts show episodic activity. So we carried out a more detailed study of NGC 2639 in which we saw that the lobes were aligned in the north-south direction, and the previously known lobes were aligned in the east-west direction. So the lobes are also highly polarized with about 21% degree of polarization. And the inner core resolves out on parsec scales to show jet emission at an intermediate angle. So we consider several models to explain the double lobes, including environmental impact, dual AGN, the precession of jets, episodic activity, etc. And our data favor the episodic activity model the most. And on this slide, I show some sources in our sample which show similar properties. For example, in the images of both NGC 3516 and NGC 4388, we can see two distinct lobes aligned along two different directions. Similarly, in NGC 2992, the second pair of lobe was identified using polarization previously by Irwin et al. In 2017. So we find that a majority of our Seyferts show tentative evidence for restarted jet activity. So to summarize, we carried out an in-depth study of two Seyfert galaxies, and we find that the jet might be playing a major role in determining the morphologies of these systems. And polarization can indeed be used as an effective tool for distinguishing between various models of origin of radio emission. The radio FIR correlation study suggests that the jet is the most likely responsible for excess radio emission in Seyferts. Finally, many of our Seyferts also show tentative evidence for restarted jet activity. Do I have time for one more slide?
Sure, go ahead.
So finally, I'd like to present just one more slide on the current work that I'm carrying out for my postdoc. So it's unrelated to my thesis, but I thought some people might be interested. So we were studying X-ray jets in 4 Mojave places using Chandra and HST data. So the motivation was to understand the dichotomy in emission models based on the FR morphology. For instance, it was known that the jets in FR1 sources prefer simple synchrotron model, whereas the FR2 sources often required an ICCMB model. So we detected X-ray emission from jets in 2 sources. One was a hybrid FR morphology blazer and another one was an FR1 source. For example, this source shown on this slide is a hybrid morphology source. The radio contours are overlaid on the Chandra X-ray emission. And the SCD modeling suggested that the ICCMB model was required for both our sources. And but again, the ICCMB model faces a lot of challenges. For instance, the gamma ray emission is over-predicted by the ICCMB model. But again, we need more data to conclusively rule out the ICCMB model because the parameter space is huge and our data is limited. Especially the HST data are just limits. Also, it was interesting that one of our sources, which was an FR1 source, still required an ICCMB model to explain the SCD. So it was previously suggested that the radio powers are more important than the radio morphology itself. And for this source, the radio power was more like an FR2 source rather than an FR1. And so all this needs to be explored in more detail. And that's where I'll stop. Thank you.
Thank you very much for a really interesting talk. You're getting a lot of claps. I don't know if you can see that. Do we have any questions? Please, yes, Mojigan.
Hello. Thanks for the nice talk. Can you go back to the slide that you were showing the relation between the AGM power and the it was the jet power, I guess, and then you also had the star formation. Yeah, this one. So you might have mentioned, so how do you estimate the AGM power on the y-axis?
So this is from, so we used the hard X-ray power from 0.2 to 10 kV to estimate the bolometric AGN luminosity, and then we used we assumed that it's 5% of it goes to winds, like feedback into the galaxy.
So my actual question is that, so you have to, most of your sources are kind of close to this one-to-one line, except for the two sources that you have down there with the power in radio being much higher than the
accretion. Yeah.
So what is special about those two sources? What is the difference between those two and the rest of your sample?
I mean, I have to like go back and look at those two sources. Now I don't remember which were those. Yeah, but like, yeah, that's something
That's
else.
fine.
Yeah.
Thank you.
Thank you.
Thank you. Do we have other questions? You can either raise your hand or put your question in the chat. Moshkin, did you have a second question, or is your hand still up from the first one?
No, my hand is still up. I need to bring it down.
Okay.
Thank you.
All right. Well, I don't see any other questions at the moment. We do have a meeting schedule for our first speaker. It was sent out to CFAY this morning. So there are time slots today afternoon and tomorrow morning. So please feel free to sign up if you would like to speak to her. And let's thank our speaker once again.
Thank you.
You're off to you.
Right, our next speaker will be SAO's very own Dan Schwartz. Dan is both easy and hard to introduce in the sense that he is a real fixture of both SAO and the high energy astrophysical community and has been for quite some time. He's been the science operations team coordinator for Chandra. He's a senior physicist at SAO. And he has been working in high energy astrophysics for over 50 years. He got his start working on gamma ray observations from balloons and OSO3, and is a widely recognized expert on X-ray jets and X-ray optics and detectors. And his presentation today will touch on the issues involved in both. Dan, if you're ready.
Yeah, I'm trying to share my screen. Am I sharing my screen?
I can see it, and I can see the whole screen.
Okay, so now I'm going to start the PowerPoint presentation.
Yes.
Do you see just the slide and not all the junk?
That's right.
Super. Okay, I'm going to start my clock. Okay, I'm going to tell you about an exciting new use of the Chandra X-ray Observatory, namely for performing milli-arcsec X-ray astrometry measurements, which gives parsec scale measurements at large redshifts. My co-authors, Anna and Christiana, have been the intellectual impetus behind this for some number of years, and they've published results comparing optical and radio positions. And here we're extending the work to the X-ray band. The wallpaper here is an illustration from a recent press release about the object that I'm going to tell you about, with the smooth Chandra data shown up here. So why do we care about the early universe? Well, we want to elucidate how supermassive black holes grow and evolve. And the reason for that is because they're apparently very well correlated with the growth of the bulge mass and with the growth and formation of galaxies themselves. So we could ask when and how do the feedback cycles of the black hole bulge mass feedback turn on? In X-ray astronomy, the current major problem is that the Chandra X-ray resolution is like 1/2 arcsecond. That's how well you can separate sources. Whereas the absolute astrometry is like 0.8 arcseconds. So that's how well you can locate an isolated source on the sky relative to other objects. This limits us to distances much larger than 5 kiloparsecs as soon as we get to redshifts that are greater than a few tenths of arcsec, a few tenths. And realistically, no X-ray telescope for the next 50 years will have vastly greater resolution than a 1/2 arcsecond to be able to do this directly. So gravitational lensing offers us a new channel of data, X-ray astrometry of high redshift AGN. The golden ticket that we'd like to find are dual or binary supermassive black holes, where binary is usually considered to be separations of less than 100 parsecs. This would tell us that mergers are, as is thought, are a viable mechanism for the rapid growth of black holes in the early universe. We'd like to measure the 3 independent X-ray, radio, optical offsets. And I'll remind you that for many years, the dominant X-ray emission from the nearby galaxy M87 was from an X-ray flare in a knot that was 60 parsecs away from the core of the M87 galaxy. So this is a very important measurement to pursue. And of course, we just heard in the last talk about parsec scale radio emission in Seyfert galaxies. Another key observation would be if we could resolve parsec scale X-ray jets. We infer relativistic jets in the cores of these objects at scales that we can't resolve due to time variations. We can resolve X-ray jets on scales of many kiloparsecs, and now we'd like to look in between to trace the X-ray jets. Also, black holes are not necessarily at the centers of their galaxies. Mergers, coalescence of 2 black holes with the emission of anisotropic gravitational radiation can lead to the ejection of a black hole from the center of a galaxy, as can interactions of triple black hole systems. So in this talk, I'll be discussing our recent publication of this source. It's from the MIT Green Bank Radio Survey, which I think goes back to the 70s or 80s. This was one of the first radio quad gravitationally lensed sources discovered with its 1950 coordinates. So this paper is published. This source is at a redshift of 3.273. That's when the universe is just under 2 billion years old. And one remarkable thing is that an observation of less than 8 kiloseconds early on in the mission and with only 24 X-ray photons has allowed us to make the following conclusions. We find that there's 2 distinct X-ray emitting sources. They're something like 80 plus or minus 80 milli-arcseconds apart. That's about 650 parsecs at the scale of 650 parsecs at the scale of this redshift. The quadruply lensed X-ray source is within plus or minus 40 parsecs, 1 sigma, of its VLBI counterpart. That's only in 1 dimension. I'll get back to that point as I go through the talk. So this is giving us unprecedented astrometry and unprecedented proper distances at such a large redshift for measurements in X-rays. So I have lost a slide. Okay, so I'm going to go through I'm going to go through how we derive this result. The first step is to make a model of the lensing galaxy. And this is based on VLBI observations of Christiana Spingola and her group, who've resolved 4 distinct sources and substructure in each of those sources. So we first create simulated X-ray sources at each of the positions of the 4 sources they've defined. We simulate the sources with SAO trace and Mark's high fidelity simulations using an intensity using 1,000 separate runs that we merge so that we have intensities 1,000 times the X-ray statistics of our actual observation. Then in step 2, when we get to this slide, we want to predict how many X-rays we should see from our simulations. So for each possible putative source position, and we take possible source positions perpendicular to the caustic along here, parallel to the caustic along here. And for each one of those, the high fidelity mass model predicts 4 exact X-ray image positions. So for example, for this source number 63, we'd see 1, 2, 3, 4 source positions. And as you go along different source positions, you would see different image positions along these streaks going here. And as the X-ray source exits the caustic, the 2 source images merge and you only have 2 images left. So along these linear arrays, we take the trial source positions, we've predicted the image positions, then we construct a model placing those simulated point sources from step 1 at the separations and with the amplitudes predicted in step 2. So here's our X-ray data. It's 24 photons associated with the source. There's a couple of background sources in this region. We bin the data in quarter-arc-second pixels, half of an ASIS pixel. So we've got an array of 28 by 26 pixels, 7 arc seconds by 6.5 arc seconds. And we take the observed number of counts in each pixel, 0, 1, 2, 3. These are small number statistics. We raster the model that we've made in step 3 in 2 dimensions in order to register the X-ray image, which has 0.8 arc seconds absolute error from just the Chandra aspect solution. And at each step, we predict the lambda sub I number of counts per bin. Then we compute the maximum likelihood as the product of the Poisson probabilities. And we take the logs so that we have the sum of the logs. And we maximize the likelihood. In practice, we're minimizing -1/2 of this quantity C. The key fact is that this delta C is distributed as chi-square. And that's almost independent of any distribution for the individual probabilities. So that's a theorem that from statistical mathematics from the 1930s, which Webster Cash published a paper on in the late 70s to apply to X-ray astronomy, where we typically have individual photons and therefore always a Poisson distribution. Originally, this source was detected by ROSAT and interpreted as being a cluster of galaxies. And of course, ROSAT has 5 arcsecond resolution, so much larger than the scale of this figure. However, since the optical galaxies were not seen, it was interpreted as being a cluster dominated by dark matter more than usual. The Chandra observations, which was a GTO observation proposed by Gordon Garamer, was published, and that revealed the point sources refuting the dark cluster interpolation. So now, as a detail in the registration, the simulated images have to be renormalized to be either in the ratio of the predicted magnifications from the lens model, or allowing those ratios to vary, constraining the sum to equal the observed number of counts. In fact, with the allowing variable intensities always gives a larger likelihood, a smaller value, because you have more degrees of freedom. So that's what we do. For each trial source position, the first stage of the likelihood is to interpolate within our raster to find the best registration of the predicted X-ray image. At the next step, we take the different trial source positions and compute the maximum likelihood of all of those to try to find the best trial source plane position to fit our data. And this shows a result where we consider that there's just one X-ray source that's inside the caustic. Perpendicular to the caustic, which is much more sensitive to position measurement because that's where the gradient of the mass potential is largest, we can seemingly measure the minimum position within about plus or minus 5 milli-arcseconds. While parallel to the caustic, where we're less sensitive, we have seemingly plus or minus 25 milli-arcsecond location. However, there's a problem with this interpretation of this data. That problem is that we get totally unrealistic image ratios. The ratio of image C to either image A or B is much smaller than predicted. In other words, A and B are much larger fluxes than expected from a single source that would be inside the caustic. And we see that this discrepancy occurs just where we would get the minimum likelihoods, and obviously allowing that extra degree of freedom of the unrealistic source amplitudes is what's lowering the likelihood. So we know microlensing can cause magnification changes, and so can time variations for that matter. Here we need the changes to be quite large, more than 3 optical magnitudes, factor of about 15, which is physically possible, but the issue is that coincidentally, both A and B need to have about the same degree of magnification. And we're noting that A and B are relatively far from this lensing galaxy. So we expect that to be pretty unlikely. And we conclude that there's 2 X-ray emitters, one inside and one outside of the caustic. So the next step is to do these likelihood computations again, but this time taking 2 sources, the color-coded sources that are outside the caustic and the same numbered sources from inside the caustic. And for the different combinations of the 2 sources, computing the likelihood. For each combination, we get a likelihood value associated with the given position in the sky. And what we do is marginalize each source over the likelihood of the other source in order to obtain 2-dimensional contours of allowed position for the given source. And those contours are shown in the next slide. So here we have our final positions. One X-ray source is located within this region here, one within this little red region to 1 sigma. In this figure, the X's are the individual X-ray photon positions as calculated according to the Chandra aspect solution. We can use our eyeball and imagination. I can imagine that this group would be sort of rigidly shifted about a half arc second. All of the X-rays have shifted about a half arc second in that direction to best agree with the VLBI position shown by these purple diamonds. The VLBI positions are registered to the ICRS coordinate system to the order of 1 milli-arcsec. So in the blow-up here, we see the X-ray positions better. X1, which must be inside the caustic, X2 outside the caustic to the 1 sigma, 90%, 95% contours. So in one dimension, perpendicular to the caustic, we've measured X1 to be within plus or minus 5 milli-arcseconds of the VLBI counterpart. Now, parallel to the caustic, the error could be something like 80 milli-arcseconds. It's very much larger. Nonetheless, even considering, say, the 90% contour range for that source, the total area inside this 90% contour is more than several hundred times less than the area if we just use the 0.8 arcsecond Chandra absolute astrometry and drew a circle of that radius. So we've really made a precedent-breaking observation. We've measured the spectra for only 24 photons, and of course it's very imprecise, but assuming a power law with only galactic absorption, we get a photon index of 0.8, which would be very unusually flat. Or if we allow intrinsic absorption of we find 1.7 plus or minus 1.4 times 10 to the 22 per square centimeter, we get a index that's more like that typical of quasars. So this spectrum gives these fluxes, ergs per centimeter squared per second. So we measure for X1, 1.8, for X2, 1.3. This is in the measured 0.5 to 7 kilovolt band. In the intrinsic 0.5 to 7 kilovolt band in the rest frame, the stronger source is really very much less luminous because it's magnified very much more being inside the caustic. So it's more than an order of magnitude less luminous. So the Rubin, the SKA, the Roman, and other facilities that are coming online soon are going to find tens of thousands of lens systems. While the finding of any one particular system depends on the systematics of properties of the mass model of the lens itself, the background quasar knows nothing about what particular lens is in our particular line of sight, and therefore we're getting a totally unbiased sample of these background quasars, truncated, of course, at the bright end by just the paucity of numbers. Only a subarcsecond telescope like Chandra or Lynx would be able to probe their structure or resolve the individual sources at all. For example, with Lynx, we would be effectively extending a Lynx megasecond observation that has sensitivity to minus 10 to the minus 19 ergs per centimeter squared per second. Could be extending it to 10 to the minus 21 ergs per centimeter squared per second, which formally could detect the Eddington luminosity of a 1,000 solar mass black hole. Well, in that era of thousands of quad lenses and a subarcsecond telescope, why would one bother to point a telescope at any system other than a lensed quasar? Thank you. So I'll take questions, and two of my slides disappeared. I don't know where they went. But
Thank you, Dan. Do we have any questions? You can raise your hand or type it into the chat. J-Sub?
Hi, can you hear me?
I can, yes.
Yeah, it's a great talk. I have two questions. First one is about you mentioning about the Chandra aspect solution. I guess you match with some other sources in VLBI images, I suppose. But I'm wondering, still wouldn't be the aspect solution precision for Chandra wouldn't be dominated by the sort of statistical error of the Chandra position itself? And that's the first question. Second question is about when you assume whether the intensity distribution is equal or whatever. If there is an intrinsic absorption, depending on the how the light bends, wouldn't that could there be some dependence on the the direction of the light coming out in the local absorption, which will lead to different flux ratios? Is that should be taken into account, or is that too small to ignore? So those are the two questions. I'm not sure I made
That's certainly feasible that in the intervening galaxy, there'll be differences in absorption that can cause different flux ratios. And also, I think I mentioned time variability, which we know is common. As for the first question about the Chandra position, in one of the missing slides, I emphasized that we need to look at systems that are quadruply lensed. So we have 4 X-ray sources, and we can overdetermine a relative coordinate system just among the X-ray sources themselves. And then, of course, related to the ICRS, or the Gaia for that matter, coordinate system via a Gaia RVLBI observation.
Okay, thank you.
Tony?
I was just wondering how do the optical images help or hurt in this analysis? I'm used to trying to get a lens model entirely out of optical images.
Well, Gaia positions, of course, would be equally good. They're milli-arcsec typically for sources bright enough that 3 or 4 images can be seen. In fact, HST, which doesn't have substantially better absolute astrometry because it's related to the old star. This is the star catalog. Also can achieve milli-arcsec relative astrometry. So, so the simple answer is yes. And in fact, Spingola and Barnowska have used HST and VLBI on a couple of other sources to show, in one case, coincidence within about 15 parsecs, and in another case, a discrepancy of 240 plus or minus 135 parsecs.
So is this model based on the X-ray data useful in interpreting the rest of the galaxy, the rest of the galaxy that's not an X-ray emitter?
I'm not sure where this question is going with in interpreting the. No, in a sense. I mean, we have to use the mass model derived from the radio observations in order to compare the X-rays to the radio. If we knew that the X-rays and radio were absolutely coincident, which we don't know. I mean, there's lots of arguments. If we knew that, then yes, then the X-ray positions could be telling us something about the mass model. But we're far from that being the case. In fact, you know, the thrust of our objectives is to try to study how well X-ray and optical and radio observations, emissions are coincident.
Okay, interesting. Thank you.
All right, we are at the end of the hour, so let's thank our speakers for a couple of really great talks, and hope to see you all again next time.